Okay, so this is 17.7 Stokes theorem. Oops, what happened here? All right, sorry. So this is 17.7 Stokes theorem. Let's just write it down. We'll talk about what it all means. We'll talk about how we use it. And pretty much the good news is we've already discussed pretty much all the background needed. So essentially, in a way, this is just a new formula where the components are pretty much familiar to you. Okay, so the setup is we have in space, we have a surface and it has a boundary. All right. So let me call this surface S and let me call the boundary C. All right, so this is a curve. All right. Then Stokes' theorem says, so first of all, this is going to be an extension of Green's theorem to kind of the surface case. All right. So in Green's theorem, the theorem was about region and its boundary. So now the theorem is about a surface and its boundary. Okay. All right. So integral surface integral S curl of f, so very, very much like Green's theorem that we saw in the earlier sections. But of course, in the previous section, the Green's theorem, the way we presented it was just double integral over a region of curl and then dA, right? Because it was just in a plane. But now the curl is a vector field, and so you can't just integrate this. It wouldn't even make sense. So what actually does make sense is this guy here, right? ds. So essentially, you could say this is the flux of the curl across S. All right, because remember, vector field dot n ds, that's the flux across the surface in the direction n. Okay. All right, well, the theorem says that this is equal to integral on the boundary f dot t ds, little s. All right. Okay, there's a major issue here that we have to talk about before we can actually do computations relating to this, and that's that this guy here requires us to have S be oriented. All right, S oriented. Let me write like this: S must be oriented. Okay. Otherwise, to have a kind of consistent normal means you should be oriented. And here, this guy tells me C has to be oriented, right? C, let me say, because it's a curve, let me say it like this: has direction. All right, but we could obviously say is oriented as well, but has direction maybe is more approachable in terms of curves. All right. Okay, so the deal is these two guys have to be compatible. All right, so you can't just pick willy-nilly any normal and any direction here. All right, so the normal, if you pick a normal for your surface, then the direction for your curve on the boundary is determined by that normal. All right, and also vice versa. If you decide you like a particular direction for your curve, then that determines the normal direction. All right, so these two guys are tied together. If you just willy-nilly use a normal on the surface side and just a random direction on the curve side, right, one of the two directions, it's very likely that you'll get negative of the correct answer. All right. All right, so how do you make them compatible? So we'll do it kind of by picture. So here's a surface, and let's say this is our surface is the upper hemisphere of a sphere, and our boundary is going to be the equator, essentially. All right. Okay, so let's say I choose a normal that's pointing like this. All right. So the question is, if I choose this normal, what should the curve direction be? All right. And as usual, there's two possible directions, right? The curve could have direction this way. The curve could have direction that way. All right. So which one is the correct one for Stokes' theorem for this equality here to be true? All right. Okay. Well, the way you do it is you take this normal and you kind of, because this normal, this surface is oriented, this normal must be consistent. So if I can just kind of shift this normal, shift this normal, shift this normal, and in essence, I'm going to shift it until I get to the boundary. Okay. And so the picture is going to look like this in this case. All right. So by the way, in this description, in this particular example, I'm using the outer normal for the sphere. All right, because it's pointing out of the sphere in a way. Okay, even though I only have half a sphere, because I do have part of a sphere, that phrase still makes sense. All right, so because I chose this normal, I can shift it all the way to the curve down here, right? And what I'm going to do now is I'm going to use the right hand rule. I'm going to put my hand so that my thumb points. I'm going to put my hand kind of, right here. Sorry, right there on my point of interest. I'm going to, so that my thumb points upwards. All right, so my thumb is like that. All right, so if I do that, my fingers are going to point, and let's say I extend my fingers outwards. Right, instead of curling them up with the usual kind of right hand rule, we like to start them out and curl them in, right? So let's do it like this. You have your thumb pointing up, pointing in the direction of the normal, and have your fingers pointing straight out. All right, so your fingers are straight. So I guess your hand looks like this. Okay, so if your hand does look like that, in this picture, it would look like this. Right? So the direction in which your finger is pointing, that's the correct normal. So in this particular example, that's the direction. So in this particular example, the direction should be that way. All right. Okay. On the other hand, if we had chosen the inner normal for this example, so that would be the normal, right? Then our hand, in order to have our thumb point in the same direction as a normal, our hand would have to look, right? Here's our thumb, and our fingers would have to point this way. Okay, and so the tangent direction would have to be that one. Okay. All right, takes some getting used to if you want to kind of visualize these, but ultimately it's relatively straightforward once you are used to it. Okay, so in this example, in the upper example, I would say n is equal to outward normal, right? Which again pretty much makes sense because we're talking about a sphere. But alternatively, you could say it's the upwards pointing normal. All right, and again, upwards means the k component of the normal vector is positive. All right. Okay, and you can see that here, the implication is that this guy here is counterclockwise. When viewed from above. All right. Right. So in other words, if you put your eye here, right, this guy, if you put your eye up here from the z-axis and you look down, what you're going to see in terms of the boundary is you're going to see a circle, right? And if you look at the normal, that's going to be, that's going to be like that, right? And so it's going to be counterclockwise motion. All right. It's very important that I said the words viewed from above, because if I put my eye down here and I view it from below, then I'm still going to see, again, just the boundary. What I'm going to see is the circle, but it's going to actually be clockwise. All right. So it's very important to say the viewed from above. All right. I think the book is a little sloppy about this. if they just say the words counterclockwise, they mean counterclockwise when viewed from above. All right. Okay. On the other hand, of course, this second example here, n is downwards pointing. In quotes. I mean, so these are all in quotes because, you know, it's kind of colloquial description. This is n here. And my normal vector here would be clockwise when viewed from above. All right. Okay, so that's something you have to be aware of when you're going to use Stokes' theorem. Let's see. So common. So this is. I mean, essentially, if we look back at Stokes' theorem, that's the only kind of real issue here with this theorem, because again, everything on this left-hand side we know, we understand. We understand the curl. We understand how to curl is a vector field. We understand how to calculate the flux across a surface S of a vector field from the last section, right? So this guy here is completely understood, right? The right-hand side is completely understood. It's something we've been doing for actually many weeks now, right? Calculating a work integral along a curve, right? Or a flow integral along a curve. So it's only this compatibility issue, which is the new thing from this kind of expression here, all right? So in a way, we could just stop this lecture right here, because essentially you have all the information you need to do calculations, all right? But there are some kind of details and kind of tricks in a way that involves Stokes' theorem that we're going to go through. All right, and one of those kind of tips or tricks is so one of the common ways of parametrization is when you have a graph, right? So you know, the surface that you're working with is the graph of a function, right? And remember the parameterization, a convenient parameterization was x of u v equals u, y of u v equals v, z of u v equals f of u v. So if you do this parameterization, then the normal is going to be upwards pointing. All right. And you can literally calculate this yourself. I think we did it actually in the last section. So this was equal to something I plus something j, f sub u minus f sub u plus f sub v, and then plus 1 times k. All right, so it's upwards pointing because it's 1 times k, positive number times k. All right. So that means if you're going to do Stokes' theorem, right, you should be using counterclockwise. Stokes' theorem, let's say Stokes' theorem, let me write it like this to be more precise. Stokes' theorem on a graph, right, with this parameterization. Right, then you should use counterclockwise direction for boundary. Okay. All right, so that's a small. I mean, and again, how do we know this? Essentially, this discussion up here. All right. Okay, so that's a small tip. Of course, if you don't remember this, you can figure it out directly yourself, right? Like I said, you can calculate. Sorry, this is TU cross TV. You can calculate TU cross TV yourself. You realize that it's upwards pointing normal, and then you can kind of go through this right-hand rule to realize then that means the boundary should be counterclockwise. All right. When viewed from above, did I say that? Again, I should always be careful when viewed from above. And by the way, this phrase makes sense because when you do have a graph, there is such thing as viewing it from above and kind of counterclockwise when viewed from above would make sense. All right, before we go into more details, let's quickly talk about what it means and why it's true. Essentially, what it means is the same thing as in Green's theorem in the plane. So remember Green's theorem in the plane, you're kind of the curl portion of the integral was calculating, kind of in a way, adding up all the infinitesimal curls at each point, right? Because curl of f is the infinitesimal kind of fluid flow around that point, right? And then the right-hand side is the flow or the work across around the boundary, right? And by the way, remember there we actually had to have the correct orientations as well, right? So, and of course that's compatible with what we talked about here. So by the way, also this version of Stokes theorem, this Stokes theorem completely covers the case of Green's theorem. It's a generalization of Green's theorem because we can think of, in Green's theorem, you're talking about a region in the plane. So you can just think of that region as living in space just on the xy plane, right? And then this Stokes theorem would be completely equivalent to Green's theorem because curl of f dot n would be curl of f dot the k direction, because your object, you're thinking of your object in the xy plane, right? So the normal is the k direction, all right, if you choose that one. And in that case, again, you would be flowing around counterclockwise around the boundary, all right? So this Stokes theorem completely encompasses Green's theorem. All right, in any case, our picture of Green's theorem was you're adding up all these kind of little curls at each point, right? And then if you do add them up, you essentially get the flow integral around the boundary, all right? And the reasoning, we talked about the reasoning in terms of kind of actually physically calculating on rectangles, but in a way you can see this just from this little picture here, right? If I do these kind of little curls here like this, right, I can see that this arrow here is pointing in a opposite direction of that arrow there, right? So inside, wherever these kind of two circulations in a way meet, right, they're going in opposite directions, so they cancel, right? So the only, let me do that in a different color. So the only ones that kind of don't get canceled are the parts which are on the boundary, right? So if I have a kind of circulation there, this guy right here in a way doesn't cancel, so it stays, right? Whereas this side here will get canceled out by a little curl over there. Okay, this is not completely not rigorous math, of course. The more rigorous math was our discussion with the rectangles, right, where we actually integrated along rectangles, right? Then we could literally see the cancellations. But this is the kind of intuitive idea behind what's going on. All right. Well, Stokes theorem, same thing. Okay, so you have these little curls like this, right? Little curls like this, and you can see if I look at this curl right there, or calculating the rotation around this point here, this one is pointing that way, but right next to it, it's pointing that way, opposite direction, and so they cancel. And so what happens again is the only kind of parts of this which don't cancel is the ones that are along the boundary. And so if you add up all these little kind of curls like this, right, only the ones from the boundary, only the portions from the boundary are going to be left. Again, very, very vague, but this is the intuitive idea. Okay, and so essentially the reason this is true is basically the same as the reason the Green's theorem was true back in 17 point whatever it was, 3 or so. All right. Okay, you can prove this rigorously and carefully, of course, in which case you would chop this guy up, you would do a parameterization, right, and then you'd have to look at parallelograms, linear approximation, but essentially you end up with the same idea of integrating along these, right? Integrating along these, and literally, again, you can see opposite directions wherever there's a meeting point in the interior, but on the boundary, nothing gets canceled out. Okay. All right. So if you have, in a way, decent intuition of Green's theorem, you have pretty good intuition for Stokes theorem as to what's going on. All right. Okay. let's talk about computation. So how do you actually compute? Well, for the left-hand side of Stokes' theorem, curl of f dot nds s, right? And again, remember, I like to use this curl notation, just writing it out, but our book really likes del dot f, right, dot n, like that. Okay, so purely notation, just keep that in mind. All right, so how would you compute this? Nothing fancy, right? It's just, like we said, a surface integral. So technically you already know how to do it. But remember, remember that we do have a shortcut in that n, if you do a parameterization, so let me go from here to here, parameterization. Right, with u and v, let's say, okay? Then n is going to be t sub u cross t sub v over length of t sub u cross length of t sub v. And then this is going to be curl of f dot that. And then ds, remember, becomes t sub u cross t sub v, like that, and then du dv. And so these two cancel out. Sorry, I should do the limits of integration. Is going to be u equals something to u equals something, v equals something to v equals something, right? Depending on exactly how you parameterize. But the important feature here is that when you ultimately integrate, things actually look relatively simple. Dot t sub u cross t sub v, du dv. Okay, where of course you're converting everything to u's and v's. All right, a small thing, of course, when I say the word parameterization here, parameterization that preserves the orientation, right? Let me write like here, preserving orientation. Okay, so if your parameterization, if this t sub u cross t sub v is not in the direction that you want, then you're going to have to pop out a minus sign. All right. Okay, so definitely be aware of that. It's really easy to make a mistake and have negative of the correct answer. So when you do a parameterization, make sure you're aware of what direction your parameterization's normal is. And if your problem has given you a normal direction, right? If they say, we want the outward normal or the upward normal or the downward normal, right? Or the inward normal, then you got to make sure that these two guys are compatible. Okay. And again, compatibility just means in the same direction, right? So it's a small thing to have to check. All right, but once we're here, this is just a integral from chapter 16, right? So early on in chapter 16, 16.2, okay? So hopefully you're comfortable with that already. So I'm not gonna continue from here. Okay, so that was the left-hand side of Stokes' theorem. For the right-hand side of Stokes' theorem, if you want to compute that, there's really nothing to talk about, right? We've been doing line integrals for a couple of weeks, for many sections now. So this is just a line integral. Right, so there's nothing fancy here, right? Just parameterize, and you're all set. Okay, and remember, this f dot t ds simplifies because the t and the ds, in a way, when you write them out in terms of dt, they kind of cancel nicely. Basically the same idea as what's going on upstairs with this curl. All right. Okay. So that's pretty much it with Stokes' theorem. From here on, just a couple kind of tips and tricks or interesting features. So here's something interesting. If S has no boundary, right, then the left-hand side of the Stokes' theorem would say integral curl of f dot n d capital S. That should be equal to the integral on the boundary, but there is no boundary, so 0. All right. Okay. What would be such a surface? For example, a sphere. For example, oops. all right? Or anything that's closed up, right? So if I say S equals the paraboloid, right, plus the cap, right, then there's not going to be a boundary, okay? All right, and in terms of, whether that makes sense or not, or the intuition here, it totally makes sense, because if you have no boundary, remember we're kind of thinking of the left-hand side integral as adding up little kind of circles like this, right? Little curls like this. And so every single one is going to have another one next to it, canceling it out, right? There's no kind of boundary where the little curl doesn't get canceled. Okay, so everything gets canceled by something else. And so you kind of expect that this guy should be 0. All right, some tricks. Let's put this in quotes. Not really tricks. Tricks is a terrible word for this, but kind of techniques that you might use Stokes' theorem to help you out in terms of computations. So one thing is sometimes if you need to compute this guy here, the total kind of circulation here, curl of f dot n ds, right? So equals question mark, right? So instead, you can do the boundary integral, right? So this seems kind of silly and kind of obvious, but if you're given a problem or you encounter a problem where you need to calculate this guy right here, right, kind of the total circulation on your surface, it might be hard, right? Maybe the integral is hard, maybe the parameterization of the surface is hard, right? If it's too hard, consider calculating instead the boundary integral, right? Because the boundary integral is just a one variable calculus integral. It's just a line integral. So it's very, very possible that that integral might be easier, all right? That one's the most obvious one. A less obvious one is the opposite direction. So you want this guy here, right? And instead, so this has to be a curve. So let me do that, right? C equals closed curve, right? And that, yeah, okay, let me just leave it like that, right? So if you encounter this kind of situation and maybe the integral is too hard, perhaps you can think about, so let me actually draw a picture, right? So something like this. Perhaps you can think about filling in a way, this curve to create a surface whose boundary is this curve, right? So let's say too hard, right? So then create a surface whose boundary is this curve, right? Let me call the surface S. So that would be S right there, right? And then calculate double integral S curl of f dot n ds instead. Okay. So this is a less obvious kind of thing to do, because oftentimes if you just see this expression, right, you're just thinking of work, right? So you just think, parameterize and try to calculate, just kind of brutal calculation, which is fine. But if it is too hard, remember that you can, in a way, fabricate a surface, right, whose boundary is this curve, and then you can calculate using a different integral instead. All right. The first one is more obvious because, well, if you literally see curl of f dot n, then you immediately think of Stokes' theorem, right? But down here, you don't really necessarily think of Stokes' theorem because it's just a regular work integral in a way. All right. So this one is something which can, go under the radar, this option here. Okay, so notice a couple interesting things. You are creating the surface, right? This problem naturally, if you just look at it up here, there's no surface in the problem, right? So naturally, there is no surface in this problem. You are creating a surface, all right? And potentially, of course, there's many surfaces that could have the same boundary, that all have the boundary, which is this curve, right? So I've drawn one here, but let's say I draw the same curve over here. I could draw another surface, maybe that kind of bumps up like this, right? That also has the boundary equal to that curve, right? So there's many possibilities, but oftentimes there's kind of maybe a couple or one obvious one that that might be easy to work with, all right? Of course, as usual, when you do create the surface, you need to have an orientation for this surface. In other words, the normal direction, right? This normal direction has to be, you have to know which direction that is. And again, that normal direction directly must be compatible with this, this direction up here. Okay, and the compatibility is through the right-hand rule that we talked about. So be careful if you are going to use this kind of correspondence here. Make sure you have compatibility there. Otherwise, you're going to get negative of the correct answer. All right. So maybe one picture example where you might see this, where you might use this idea, is let's say I want to integrate. Let's say I have a plane, right? X plus 2y plus 3z equals 6, right? So this is a plane that passes through, let's see, when that's x, y, z. When y and z are 0, x is 6. When y is 0, when x and z are 0, y is 3. And when z is 0, so when x and y are 0, z is 2. So this is a plane, or this is a plane that looks like that, all right? So if you want to integrate along here, right? Here, here, there, a work integral, right? So if you want to calculate, so let me call that C. If you want to calculate f dot t ds along C, how many integrals do you have to do? You have to do three separate integrals, right? Because this parameterization here is different from that parameterization there, is different from that parameterization there, right? So this guy is equal to 3 integrals. On the other hand, if you integrated, this guy here, curl, right? Where I took S is equal to the plane, right? So that plane right there, then it's just one integral, right? You parameterize the plane, which is relatively straightforward, right? Because the equation of the plane is super simple. In fact, the Jacobian is going to be just a constant number, right? So your compensation factor is just a constant number. So it's very possible that this integral here is going to be easier. Okay. Again, you got to make sure your compatibility is correct, right? Let's see. If I've drawn it like this, where I want to integrate the line integral in these directions, then my normal direction is going to have to be pointing upwards like that. All right. Out towards, in a way, out towards you. It's kind of hard to outwards. All right, towards you. Okay. So that's a concrete example where it could very well be easier to do the surface integral as opposed to several line integrals, right? Ultimately, all of these are possibilities that you could consider, but it's not necessarily the case that, for example, this surface integral is easier. That completely depends on what the curl is, right? And of course, the line integrals depend on, how difficult they are, depend on what this guy is in here, right? It could be that ultimately, when you write out all the expressions, this integral is too hard, right? But it's just something to always keep in mind, okay? Well, on the other hand, right, if you do know something about the curl, if you know, for example, that the curl of f is 0, right, just if by looking at f, it's simple enough that you recognize the curl is 0, then you can go from the line integral, the line integral is equal to this, the curl is 0, so immediately your answer is 0, all right? Okay. So one more possible kind of trick or tip or trick is, let's say you need this guy here. Right? And let's say the surface is, kind of horrible, right? So something like this, right? And let's say its boundary is just a curve in the plane, right? So here's my picture. So it's just a curve in the plane. Okay, so C, S, let's pick, let's say the normal is that way, right? In that case, the curve tangent direction would be that way. And let's say again, this is in the plane. All right, it just happens that the boundary of this horrible surface is on the plane, right? So it's easy to make an example like this, right? I could take a graph of a function as my surface, and I could say, okay, I want to calculate this curl integral, this kind of circulation integral, but I'm only interested in the part of the graph which lies on or above the xy plane, right? In that case, the parts that touch the xy plane is going to be my boundary, right? And that boundary is going to be a curve that lives entirely in the xy plane, okay? All right, so from here you might say, okay, that means I can do the integral instead on the curve, right? Integral C f dot t ds, right? And that might be easier because it's just a curve in the plane, right? But if this guy turns out to be too hard, you have another alternative in that you can choose a second surface, that guy right there, right? Fill in that curve in the xy plane only, right? So let me call that guy S2. Oops, S2 like this, right? So instead, right, because S2's boundary is also the curve, then this guy here is equal to double integral curl of f dot n d capital S over S2, right? So maybe the first integral is too hard because there's a terrible graph or whatever. Maybe the second integral is too hard, right? Because of the structure of f, for example, right? So you could do this integral down here instead, okay? And perhaps this integral again is easy because it's just a flat region in the plane, in the xy plane. Okay, so again, that's another option that you might have. Now, if you are going to do this, you better be careful, again, as usual, about compatibility, right? So if I've chosen, for example, in the initial problem that the normal here should be pointing upwards like that, right? Then that means, like I said, the curve has orientation this direction, counterclockwise when viewed from above, right? So let me draw actually another of them right there, right? Counterclockwise when viewed from above. So now, what is the orientation of this plane here? So if you're not careful, right, and let's say you pick the orientation for this plane, this S2 down here, that points upwards like that, right, the k direction, then it's actually not going to be correct, right? When you put your thumb, if you shift this, let's say to that point right there, and you put your hand there, right, your thumb in the direction of that normal, it's not your fingers are not pointing in the right direction, right? So actually, you're going to have to choose this direction for your normal, all right? So this normal here, you want to be careful, right? In this particular example, n points in the minus k direction in this example. All right, so definitely be aware of that because again, if you naively just choose the k as your normal, right, k direction as your normal, you're going to get negative of the correct answer. All right, so be careful when you're using these tricks. As usual, the normal directions can cause some trouble. All right, so you'll see some of these tips and tricks on the homework. I think that's pretty much it. I guess I think I forgot to say. Well, you kind of already know this. So I'm going to write down Stokes' theorem again. Curl of f dot n ds is equal to integral f dot t ds. Right? This is a version of the fundamental theorem of calculus because here you have a derivative of capital F, right? And I'm going to put this in quotes, right? Because it's not literally the derivative, right? There's no such thing as saying the derivative of a vector field. But the curl involves taking derivatives, right? So we can think of this as a derivative of F. This is a region, right? And this guy is the boundary of that region. Right? And here there's no derivative. So again, this can be thought of, or should be thought of probably, as an extension of the fundamental theorem of calculus, right? A to b f prime dx equals f of b minus f of a, right? Your picture here is a to b. Again, the left-hand side, you're integrating over a region. The right-hand side, you're only looking at the boundaries of the region, right? On the left-hand side, you have a derivative. On the right-hand side, you have no derivative. Okay. All right. So that's Stokes' theorem. So super useful in terms of if you're actually practically studying stuff like fluid flow and things like that, right? Kind of circular flows are very important, right? Like vortices and stuff like that. And this is literally the kind of stuff you're computing, when you talk about Stokes' theorem, right? The curl, right? The kind of circulation integral on this right-hand side, right? I guess our book likes to put the little circle there. So super useful, super interesting. Next section, our last section, is going to be the divergence, an extension of the divergence theorem. So in a way, we'll have two different extensions of Green's theorem for each version of the two versions of Green's theorem.